Welcome to Physics with Joe. Light is one of the most interesting and fascinating things in the entire universe. In fact, light is so interesting that we need to use different models to describe all the various properties that light can exhibit. In the ray model of light, we treat light as traveling in straight lines called light rays, and we use the ray model to describe how mirrors and lenses work. In quantum mechanics, we use the photon model of light, where light behaves like a particle, and we use the photon model to describe photon-particle interactions such as Compton scattering and the photoelectric effect. And then finally, we have the wave model of light, where light behaves like a wave. And we use the wave model to describe diffraction and interference. And in today's video, I'm going to talk about Young's double-slit experiment, also known as double-slit interference, in which light traveling through two closely spaced narrow slits can exhibit both constructive and destructive interference, which is a property of waves. So without further ado, let's jump right into it.
In my previous video, I talked about wave interference because of a path length difference. So I have two sources of waves, and those sources are initially in phase, which means they're leaving the two sources at exactly the same point in their cycle. So both waves are peaking at the same time, reaching a minimum at the same time. Even though the two sources are initially in phase, if they travel different distances in reaching an external point P, they can arrive at that point either in phase to produce constructive interference or out of phase to produce destructive interference. And whether or not they produce constructive or destructive interference has to do with what's called the path length difference. How much farther waves from one source travel compared to waves from the second source. I have two different animations showing this interference because of a path length difference. And since it's important in two-slit interference or double-slit interference, I just want to quickly review the important points. So in the bottom, I have two sources of waves, A and B. Those could be water waves, they could be sound waves, they could be light waves, it doesn't matter. And I have a point P here, which initially is right smack in between the two sources. So AP is the distance of source A to point P, BP is the distance of source B to point P, and the path length difference is basically the absolute value of AP minus BP. In essence, it's how much farther light or waves from one source have to travel compared to waves from the second source. In this case, point P is equally distant from each source. So my path length difference is 0. And you can see the end result is I get fully constructive interference. The two waves add together at point P to produce a wave that has twice the amplitude of either wave. And again, that's fully constructive interference. And that's also shown in the animation at top. I have two sources of waves that are initially in phase, so they're leaving the sources exactly at the same point in their cycle. And here, they're arriving at an external point P, still exactly in phase, producing fully constructive interference. Now, since a wave repeats itself after traveling one wavelength, if instead of a path length difference of 0, it has a path length difference of one wavelength. So waves from one source travel exactly one wavelength farther than waves from the second source. What you'll see is that I still have fully constructive interference. So at the bottom here, you can see in white, this is the path length difference, how much farther in this case waves from source B travel compared to waves at source A. If that path length difference is one wavelength, then the two waves that start off in phase are still going to arrive at point P in phase and produce fully constructive interference. And again, since a wave repeats itself after traveling one wavelength or two wavelengths or three wavelengths or so on, if the path length difference is two wavelengths, again, I end up with fully constructive interference. Waves from source P travels, or waves from source B travel 2 wavelengths farther than waves from source A. So let's look at that at this top animation. If I have waves from the bottom source traveling exactly 1 wavelength farther, so here in red you can see the path length difference, which is how much farther waves from the bottom source have to travel compared to waves from the top source. That is 1 wavelength. And again, they started off in phase, and they're arriving at a point P still in phase to produce fully constructive interference. So anytime the path length difference is an integer number of wavelengths, so if delta R, which is what we use for the path length difference, is 0, or 1 wavelength, or 2 wavelengths, or 3 wavelengths, I end up with fully constructive interference. If, on the other hand, the path length difference, let's say, is half a wavelength, then what ends up happening is even though the waves start off in phase, they arrive at a point P exactly out of phase and produce fully destructive interference. So in this bottom simulation, I've got waves from source A traveling exactly half a wavelength farther than waves from source B. And you can see that at point P, when I add the 2 waves together, I get fully destructive interference. In essence, I get a wave with an amplitude of 0. You can see the same thing up top in this top simulation. The sources are initially in phase, so their waves are leaving the 2 sources at exactly the same point in their cycle. However, you can see they are arriving at a point P here exactly out of phase to produce fully destructive interference. So any time the path length difference is a half a wavelength, we end up with fully destructive interference. And again, since a wave is repeating itself every wavelength, if instead of a half a wavelength path length difference, the path length difference is 3/2 of a wavelength. So if the path length difference is 1.5 wavelengths, again, I have the 2 waves arriving at point P exactly out of phase to produce fully destructive interference. And again, I can show that at the very top one. In this case, the wave is traveling 1.5 wavelengths farther from the bottom source than it is from the top source. And if I freeze this, you can see that I have the difference in path length 1.5 wavelengths. So anytime the difference in path length is a half a wavelength, or 3/2 or 5/2, we end up with fully destructive interference. Now this is important because in double slit interference, what we basically have are 2 sources of light waves, and if those 2 sources travel different distances, I can end up with either fully constructive interference, which is going to result in a bright spot we call a bright fringe, or fully destructive interference, which is going to result in a dark spot, basically no light whatsoever, and we call that a dark fringe. So let's take a look at the basic setup of Young's double slit experiment, or two-slit or double slit interference. The basic setup of Young's double slit experiment, or double slit interference, is I have a coherent source of light. Generally we use a laser beam, but when Young first did this experiment in the early 1800s, he just used sunlight passing through a single narrow slit. This coherent light is then incident upon 2 closely spaced narrow slits. As the light passes through the 2 slits, the light will spread out because of diffraction, and then the light passing through the 2 slits will then hit a distant screen, and depending upon whether we have fully constructive or fully destructive interference, we end up with a series of bright fringes where we get fully constructive interference, and dark fringes where we get fully destructive interference. Right between the 2 slits, we end up with what's called the central maximum. That's where light from each slit travels the exact same distance, so the path length difference is 0, ending up with fully constructive interference. Now we're also going to get fully constructive interference when light from one of the slits travels 1 wavelength farther, or 2 wavelengths farther, or 3 wavelengths farther, and so on, than light from the other slit. For example, the very first fringe, the very first bright spot above or below the central maximum is where light from one of the slits travels exactly 1 wavelength farther. We call that the first order bright fringe. The second order bright fringe, the second fringe on either side of the central maximum, is where light from either slit travels exactly 2 wavelengths farther than light from the other slit. And I end up with bright spots or bright fringes anytime light from one of the slits travels an integer number of wavelengths farther than light from the other slit. And then I will end up with what's called dark fringes, when light from one of the slits travels a half a wavelength farther, or 3/2 of a wavelength farther, or 5/2, and so on. That results in fully destructive interference, and we end up with what's called a dark fringe. And again, this is all based upon a path length difference. Anytime the path length difference is 0, or 1 wavelengths, or 2 wavelengths, or 3 wavelengths, and so on, I get fully constructive interference, a bright fringe, and anytime the path length difference is a half a wavelength, or 3/2, or 5/2 of a wavelength, and so on, I end up with fully destructive interference, or a dark fringe. When looking at double slit interference, there's 3 main variables that we always use, so let's just quickly define them. Theta is always the angle measured from in between the 2 slits, the middle of the double slits, to a point on the screen. That point could be a bright fringe, a dark fringe, or something in between, but theta is always measured from the middle of the 2 slits to the screen. D is the distance between the middle of the slits. So in essence, how far apart the double slits are. And then finally, L is the distance from the double slit to the screen, where we're going to be looking at the interference pattern. And the key to 2-slit interference in deriving the equation for the location of the bright and dark fringes is that if the slit to screen distance, if L, is much, much greater than the distance between the 2 slits D, which inevitably it always is in any practical setup, then the light rays coming from the 2 slits are practically parallel, and we can express the path length difference delta R just in terms of D, the distance between the slits, and theta, the angle from the middle of the slits to the screen. And just from a little bit of geometry, what you can show is that delta R, the path length difference, is always given by D sine theta if L is much, much greater than D. So my path length difference can be simply expressed as D sine theta. Now that we know we can replace delta R with D sine theta, the condition for fully constructive interference, which will produce a bright fringe, instead of delta R equals m lambda, now becomes D sine theta equals m lambda. And we often use the subscript m with theta just to indicate the angle for different fringes. M equals 1 is the first order fringe, m equals 2 is the second order bright fringe, and so on. So if I want to know the angle at which bright fringes is going to occur, then I just need to solve sine theta m equals m lambda divided by d, where again, m is called the order of the fringe, lambda is just the wavelength of light that we're using, and d is the distance between the slits. Similarly, the condition for fully destructive interference, instead of delta R equals m plus a half lambda, becomes d sine theta equals m plus a half lambda, or d sine theta m equals m plus a half lambda. This will give us the conditions necessary for fully destructive interference or for a dark fringe. So if I want to know the location of the dark fringes, I just need to solve sine theta m equals m plus a half lambda divided by d. So let's take a look at calculating where the bright and dark fringes will be in this double slit interference simulation. So in this simulation, I have light of wavelength 600 nanometers arriving at the double slit. The spacing between the slits is 2000 nanometers, and what you can see is the location of the bright fringes and dark fringes. Couple things just about this simulation. One, as you can see, it's showing a curved screen. Generally, we're not going to have a curved screen when we're doing this in the lab or in a classroom. What we'll have is a flat screen that we're projecting the interference pattern on. And also, just in terms of notation, notice we have K's here. This particular simulation, instead of using d sine theta equals m lambda as the condition for the maximum, they are using d sine alpha equals k lambda. Exact same thing. The condition for the maxima is d sine theta equals 0, or 1 wavelength, or 2 wavelengths, and so on. And then also, instead of d sine theta equals m plus a half lambda for the condition of the dark fringes, where m equals 0, 1, 2, dot, 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 this simulation is using d sine alpha equals k minus a half lambda, where k is 1, 2, 3, and so on. We still get the exact same condition that d sine of the angle is equal to a half a wavelength, or 3 halves, or 5 halves, and so on for dark fringes for destructive interference. So if I want to know what are the location of the bright fringes, well, the m equals 0 bright fringe, the central maximum, is always going to be located at 0 degrees, because I'm basically solving sine of theta equals m lambda divided by d, where m equals 0. So the sine of 0 is 0 degrees. So we always have the central maximum at 0 degrees. Now, if I want to find what is the angle at which the first order maximum occurs, the m equals 1, then again, I'm solving for sine theta equals m lambda divided by d, but I'm plugging in m equals 1. So with m equals 1, lambda equals 600 nanometers, and d equals 2000 nanometers, what I get is sine theta 1 is 0.3. Solving for theta 1, what I get is 17.5 degrees. And again, if I wanted to know what is the angle of the second order maximum, m equals 2, then I'm solving sine theta 2 equals 2 times the wavelength divided by d, the slit spacing. What I get is sine theta 2 equals 0.6, or theta 2 is 36.9 degrees. So if I go to 17.5 degrees, that is the angle at which my first order maximum occurs. If I go to 36.9 degrees, that's the angle at which my second order maximum occurs. And then we could figure out the angle for the m equals 3, the third order maximum, third order bright fringe, and what we get is 64.2 degrees. Notice there is no m equals 4 bright fringe. Why is that? Well, if you tried to solve sine theta 4 equals 4 times the wavelength divided by d, what I get is trying to solve sine theta 4 equals 1.2. That has no solution. So we can only have bright fringes or dark fringes that give us the sine of an angle which is less than 1. So you can actually use this to figure out exactly how many bright fringes are going to be produced by a particular setup. So for example, if I change the spacing between the slits to 1500 nanometers and I still have a wavelength of 600 nanometers, how many bright fringes are going to be produced? So I've got a wavelength of 600 nanometers. I've got the spacing between the slits is 1500 nanometers. What do you think? How many bright fringes are going to be produced? If I ever want to know what is the highest order bright fringe that'll be produced by a particular double slit experiment, then all I need to realize is that sine theta always has to be less than or equal to 1. And since the condition for bright fringes is sine theta equals m lambda divided by d, I know that m lambda divided by d always has to be less than or equal to 1, or m has to be less than or equal to d divided by lambda. So if I put in 1500 nanometers for d, 600 nanometers for the wavelength, then I know m has to be less than or equal to 1500 nanometers divided by 6 nanometers. So m has to be less than or equal to 2.5, and since m always has to be an integer, m equals 2 is the highest order bright fringe that'll be produced. So I'm going to have, in this particular case, 5 bright fringes. I've got the m equals 0, which I'm always going to have, and then m equals 1 and 2 on either side of the central maximum. One final point about double slit interference is that when you are looking at the results of an experiment or actually running a double slit experiment in a lab, you're not usually measuring the angle theta to a specific bright or dark fringe. Rather, what you're measuring is how far away on the screen a particular bright or dark fringe is from the central maximum. So for example, in this setup, here is my m equals 0 central bright fringe. That's right in between the two double slits. And then on either side, I have my first order, my m equals 1 bright fringe. I've got my m equals 2 bright fringe, and so on. And usually what we can measure is how far apart the first m equals 1 fringe is from the central bright fringe. So it's useful to have an equation which tells us how far away a specific fringe is on a screen from the central bright fringe. So let's take a look at how to calculate that distance y. So shown here is a simplified version of Young's double slit experiment. Remember, we've got d is the distance between the two slits, L is the distance the screen is from the double slits, theta is the angle measured from in between the two slits to a point on the screen, and ym is the distance from the central bright maximum to a point on the screen. And that could either be a bright fringe or a dark fringe. Just from geometry, since we have a right triangle, we know that tangent of theta is opposite divided by adjacent. Or in this case, tangent of theta equals ym divided by L. Or if I solve for ym, which again is the distance from the central bright maximum to either a bright or dark fringe, that equation is ym equals L times the tangent of theta. And the angle theta we use is going to depend upon whether we're looking at bright or dark fringes. Remember, the condition for bright fringes is sine theta m equals m lambda divided by d. The condition for dark fringes is sine theta m equals m plus a half lambda divided by d, where in both cases m can be 0, 1, 2, 3, and so on. So to get how far away a bright or dark fringe is on the screen from the central bright maximum, we first solve for the angle theta of the bright or dark fringe, and then we can use ym equals L times tangent of theta. Well, that is it for today's episode of Physics with Joe. Thank you so much for joining me, and until next time, happy physicking.